Hello again. It's another clickbaity title, MOND on my mind. MOND is, you can think of it as a competing postulation to dark matter. So MOND is MO for modified, N for Newtonian, and D for dynamics. And we'll get into what all that's about. So why do we need dark matter or MOND? Seems like if we look at the stars that are on the outer edges of galaxies, as you orbit something like, a satellite orbits Earth, as you go higher and higher, the orbital velocity tails off. It takes, it's actually orbiting slower. This is how you get to like geosynchronous and geostationary orbits. If you pick the right rotation of the Earth with the right speed of the satellite at the right altitude, it just kind of stays there as you go around. The same thing should be happening with stars as they orbit the supermassive black hole at the centers of galaxies. This is called the Keplerian decline in galaxy rotation curves. So as you go out farther from the core of the galaxy, your orbital velocity should get lower. And it gets out to a certain distance, and then the orbital velocity doesn't keep tapering off. It just kind of like plateaus. And stars can be further out and they're not getting appreciably slower. So they need some way to explain the observations that they're seeing. What I've got pictured here is the pinwheel galaxy, Messier number 101. This is a composite picture from the Subaru telescope and the Hubble Space Telescope. And you can see how the arms kind of sling out and there's stars towards the outer edge of the arms. And as you get further from the center, your velocity should be declining. And as you get way out on the end, it should really start to decline. But it's not. It kind of gets to a certain radius and then it doesn't go faster. It doesn't get any slower is the problem. So this dark matter stuff, how long have we been talking about something that might be an effect that's unseen? It goes all the way back to 1884. You know that guy that's associated with that very low temperature, Kelvin, Lord Kelvin? He said a long time ago in 1884 that back before we knew that, other stars don't orbit our sun and that galaxies exist and that there's multiple galaxies, he said, if I just look at the dispersion of stars orbiting our sun, which they aren't, and I evaluate that, then that dispersion seems to have an issue. I can calculate out how many stars might be orbiting the sun, which it doesn't, to be about 1 billion stars within 1,000 parsecs of the sun or of the Earth. And so that was an early estimate of maybe how many stars are in our galaxy, which it wasn't known to be a galaxy at the time. That stuck for a while, that there might be 1 billion stars in the Milky Way. Turns out there's more than 100+ billion stars. As we find more and more, it's more than 200 billion at this point. When you're working with whatever you know, and that's all that you know, and you don't have all these advancements that will come down the pike in the future, you can see that something wasn't quite right. The observations didn't match the current explanations. So he just said, this may be due to unseen dark bodies. Now, it wasn't until 1916 that we first started talking about black holes. And it wasn't until 1963 that we talked about supermassive black holes at the centers of galaxies. So he was seeing this effect in his calculation of a rough approximation of how many stars would be orbiting the sun, which would be essentially in the Milky Way. So you just thought Lord Kelvin had, temperatures on his mind. Nope, he was also studying how many stars are up there. Now, where do we get the phrase dark matter from? Fritz Zwicky in 1933. He came up with the phrase, now this is in German, so I may get it wrong, Dunkelmatter. That's dark matter. He was using something called the viral theorem. When you want to calculate how many of something there are, and you don't have a direct sampling of how many there are, you take an approximation and you say, within that sample set, I know there are this many. And if I just extrapolate the sample set to a very large degree, then I can calculate how many there ought to be. This is the viral theorem. And in order to do that, to calculate that uniformity that it could, extrapolate over the entire galaxy or the entire universe, they made a presumption. The presumption was that there was this stuff called cold dark matter, or the cosmological constant lambda, that is used to say, well, we know how much stuff is out there, but our observations don't match that. So we'll come up with this fudge factor called the cosmological constant to say everything's just like what we've seen so far. Nothing is different. Everything is uniform. And they made the assumption that all the stars that they saw back in 1933 were the same, and that throughout the galaxy, throughout the universe, everything's the same. So if I want to extrapolate out like an area of sky, I can extrapolate that out, 360 degrees by 360 degrees. And now I can come up with a very much ballpark number of how many stars there are in the universe. Assuming that back in 1933, which they just figured out that, hey, maybe there are other galaxies. They had no infrared observing capability like we have with the James Webb Space Telescope to go, oh, well, that galaxy is more redder than this galaxy, and that galaxy is more bluer than this galaxy. And it doesn't have to do with the Doppler shift. It has to do with that galaxy has more red stars in it. That galaxy has more blue stars in it. So the constant isn't a constant. But even today, we still use the lambda cold dark matter, or Lambda-CDM, to estimate how much matter there is in the universe. Then Vera Rubin came along in 1978 and started doing actual observations of stars way out in the radial arms of spiral galaxies. She couldn't do this for the Milky Way because we can't see the other half of the Milky Way because the central disk obscures our ability to see all the stars at the far edge. And we're in from the edge, so we can't look all the way out to the edge behind us, so to speak. So the galaxies that she sampled were actually only spiral galaxies and other than the Milky Way. She did come away with this conclusion that as the radius of the star moves out from the central part of that galaxy, from its central bulge, the velocity doesn't keep going down as you go further and further out. It actually starts to go down and then just kind of levels off and plateaus. So that's why we needed dark matter originally, was what's slowing things down? Got to be something out there that has a lot of gravity that's slowing things down. But since they couldn't see it, it was dark. There you go. Matter produces a gravitational field. We can't see it, so it's dark. Therefore, it must be dark matter that is causing this effect. So whenever they make calculations, especially computer simulations, anything that doesn't fit, in other words, a simulation doesn't match an observation, you've got something left over. What do you do with this something left over that will make the two things line up? Maybe not perfectly, maybe not dovetail, but just get in the same ballpark. And so that's where you get, the fact that the cosmic microwave background differed from the optical observations of the composition of the universe. And so they said, well, must be dark matter. Or we can add a fudge factor to the cosmological constant that as things get farther out in a galaxy, the effect of whatever this unknown thing is happens. Now, nobody wanted to come along and say, well, why don't you just correct your observations? Why don't you correct your simulations so that they matter, they're closer fitting, which is the W.C. Fields line of, go away, kid, you bother me. Apparently they don't want to be bothered. So today we have two popular postulations as to why for doesn't this match? One is dark matter. And if you look at dark matter, you'll find that dark matter is something that itself is not highly affected by baryonic matter. This is like elements, atoms, particles, the stuff that things are made of. Dark matter does not seem to be appreciably affected by that. However, there's enough of that stuff that we can't detect that it's affecting us. It's affecting our baryonic matter. And the claims of how much dark matter there is in the universe varies anywhere from 22% to 86% of the universe. 86% of the universe is undetectable. Okay. For spiral galaxies, they're saying that there is a halo of this invisible dark matter that starts sort of at the center and is a sphere that bulges out and encompasses all the way out to the radial arms. That way, the dark matter gravitational effect can affect everything in the galaxy. But if they said it extended way beyond the galaxy, that would cause galaxies moving between each other, like towards or away from each other, to be affected by that same force, that same presence. And they didn't want that to happen. So the halo only extends to just beyond where they need the stars to be affected. It doesn't go any further. So it's a halo, has to be there, but it can't be too big. Modified Newtonian Dynamics basically said, as things get further out, the parameter by which gravity affects their velocity changes. So it's no longer a constant, it's an algorithmic parameter that if you take the radius into account, the value changes, and that's what's causing the stars not to behave as you're observing them. So basically they added a radius variable fudge factor. That's MOND. Either can be used to explain what the actual observations are. And yet they came up with another one. This one I learned about this week, naked quantum singularities. Think of it as primordial black holes left over from the beginning of the universe, except very, very tiny ones. And there's just so many of them. Now, the only way you could have something like that come into being is back before baryonic matter came into existence. It was all just roiling energy, and you can have a collapse on that scale, and now you've got black holes. But the moment that you collapse to a black hole, you've taken energy out of the equation. So maybe the condensation of the roiling energy is from the primordial black holes, the large quantity of them, and that caused all the matter to coalesce and produce stars, which after generations produced planets and things like that. But such large gravitational collapses, in order for them to exist, they would have to be left over. We have no evidence for that. There are no small-scale black holes. We have supermassive ones, but those we know about. Those we know are at the center of galaxies. We also have what is known as stellar mass black holes. Those are from smaller stars out in the galaxy that do collapse in, and they produce black holes. And if there's nothing else around them, they're called rogue black holes because they're not feeding and they're moving around at whatever velocity they're moving around at. But this is another example of, if you can't explain the difference between a calculation and an observation, come up with something new. Naked quantum singularities. Something, once again, invisible causes it. If you think a naked quantum singularity that's a primordial black hole isn't bizarre enough, they're now saying that maybe the cosmological constant is making the cold dark matter too hot. We've got the temperature off. It's actually colder than we thought, and therefore they're calling it cold dark matter. So the reason why you can't detect it is there's less energy being emitted than would normally be the case for a black hole or a supermassive black hole. But we can detect black holes as rogues. We can detect black holes at the centers of galaxies very easily. But somehow this other dark matter is black holes that are too small to be detectable. How come they aren't affecting other things? If they're really dark matter black holes and they're small, then they should be creating gravitational lensing. They should have things orbiting them, like we can observe over a 20-year period stars orbiting the supermassive black hole at the center of the Milky Way, how come we don't see any other things orbiting these small black holes? That's because the huge gravitational field that a black hole should have isn't what they have. These are smaller black holes. They're ultralight dark matter. So they're microscopic and they're black holes, but they're really, really tiny black holes, so they don't exert a lot of gravitational effect on anything. And I remember reading that before ultraviolet was detectable in the electromagnetic spectrum, we had to wait for technology to be developed that would detect it. We could see that certain rocks would glow in certain forms of light coming from the sun that could be filtered. So we kind of knew there was something up there, but we couldn't measure it. We had to create technology that allowed us to measure it and image it and such. So I'm fine with waiting until something is invisible is detectable. But the ever prevalent search for dark matter reminds me of a story about conversations with a giant invisible rabbit, for those that are into old movies. Or someone once said, there's a slim difference between the invisible and the non-existent. So maybe MOND and dark matter aren't really the answer. Maybe there's something else. But in the meantime, since we're basing dark matter and MOND upon this cosmological constant called lambda, is it actually a constant? And if so, should it be adjusted periodically based upon the amount of observations that we do? So this is an HR diagram. This shows in the Milky Way, not in other galaxies, which could be redder or bluer. In the Milky Way, we had an understanding of how many are blue stars, how many are red stars, orange stars, sort of main sequence yellowish stars like our sun. And we had quantities for these things. Well, it turns out as we improve our technology, we're finding that there are a lot more orange and red stars in the Milky Way than there are blue and yellow stars. So the cosmological constant that we came up with should be adjusted. And if it's adjusted, would you still need dark matter or MOND? So in science, when your observations don't match your presumptions, like the quantities of different colors, different sizes, different masses of stars in the Milky Way does not match where we thought they were, the quantities that we did have, then we should go back and reevaluate them. But we got a good bead on things, as the saying goes, and nobody wants to go back and adjust the constant because we now have observations that say should be a lot more red and orange in there. So when they did the dark matter evaluation of galaxies, not this galaxy, other galaxies, what were they looking at? Were they looking at all possible galaxies? How was their sampling evaluated? Well, first off, there's two kinds of galaxies. There are spiral or arm galaxies, and there are galaxies without arms, sort of spherical, come in two varieties called elliptical and lenticular. They only looked at spiral galaxies because the light was better. The old joke, what are you looking for on the ground? My contact lens. Where did you lose it? Over there. Well, why are you looking here? Because the light's better. There's a street light overhead. Same sort of thing. If they wanted to look at stars on the outer edges of galaxies, you needed to have a galaxy where those arms made it easy to spot the stars in the outer edge, and the central bulge made it easier to know approximately where the center of the galaxy was, so they could judge the radius to see how the stars were moving at a not as expected velocity as you got further and further out. So they were only looking at spiral galaxies. They were not even looking at this galaxy. They had to take into account the Doppler shift of the center of the galaxy to know how fast the rotation was, because if the rotation is faster, then it'll sling the stars out further. Just like, centrifugal, centripetal, whichever one you want to call it, the rotational force. They made the assumption that if the galaxy had no arms, if it was spherical, that maybe there's no dark matter halo. Maybe that's why it's spherical. So they predicted that the curves should rotate as expected. And then they started doing spectroscopic analysis in the X-ray band of spherical galaxies. And they found out, oh, look, they have the same observational issue in X-ray on spherical galaxies, the stars out at the outer edge, as they did with spirals. So all of a sudden, spherical galaxies went from having no dark matter to having pretty much the same dark matter as any other galaxy. So things change when observations come along. So if observations don't match your predictions, you need to change them. So far we've seen door number 1, dark matter, door number 2, MOND. I've got a door number 3. This is just a postulation. When a star is flung out to the outer shell of an elliptical or spherical, or flung out to an outer arm of a spiral galaxy, maybe there's a point at which the amount of energy in that star exceeds the ability for that central gravitational field or even a local arm gravitational field to hold it in check. It gives it that last unk, and now it kind of like starts to move out on its own, kind of like a hammer throw. The hammer thrower spins the hammer around, and it won't go any faster unless he's stronger, or unless the hammer's out on a longer rope or weighs more. It just isn't going to go anymore until he releases it. Now, when he releases it, it starts moving away from him at whatever velocity the amount of energy put into it dictates. So moves away at a speed. Now, in a hammer throw, you've got air resistance and gravity and things like that that are going to slow it down. But if the thing that has the outward energy is a star, all it's got is whatever the local gravity is around it in that part of the shell or the arm. And if it's not enough, then it will move out to a certain distance where it doesn't have enough energy to move away further. And this what I've called galactic gravitational retention threshold. It gets out to a certain distance and then things plateau, and they're not going to get any slower. They're not going to be any faster, but they're not going to get any slower. So GGRT is another explanation. It doesn't require invisible dark matter, and it doesn't require you to fudge Newtonian physics. Now, this will be just enough, but not too much. If you know back to the early solar system, you'll note that Jupiter and Saturn were much closer to the sun at one time, and because of shuffling of gravitational forces, it caused Jupiter and Saturn to move farther out. When they moved farther out, they didn't have a lot of energy. They had just enough to get them where they are now, but they didn't have escape velocity to leave the solar system. So they moved out, given the rotational velocity of the sun and all the other gravitational items that were causing them to pull in that direction. And when they expended all that energy, it settled them nicely into the Jupiter and Saturn orbits that we know today. They didn't leave the solar system. They just accelerated out and then plateaued. And that plateau became their orbits. Same sort of thing. If I'm a hammer thrower and I'm spinning it around, if I can make myself rotate faster, I'm going to add more force to the hammer before I release it. If I make it longer, if I make the rope longer, if I add more weight to it while I'm still spinning at the same speed, when I release it, it's going to go farther. So there are parameters associated with the release and what's left of it. So we can have stars that don't escape a galaxy, they just move out and then they get into a stable orbit. That's the plateau point. So how do we verify this postulation? Look at other galaxies. If this really is something, then evaluate the radial distance of stars from either the spiral bulge or elliptical shell of other galaxies. If it's a galaxy that has, let's say, a bigger supermassive black hole at the center, then it's going to have more gravitational field. If it's got a greater spin rate, it's going to have more greater gravitational effect. If the outer arms are denser, or if the outer shells are denser, more localized gravitational effect. And this one's interesting, whether or not the galaxy is feeding. If the galaxy's supermassive black hole is feeding, it's a quasar, quasi-stellar radio source. If it's feeding, it will actually be subtracting material from the central mass of that galaxy and spewing it out either as relativistic jets out the poles of a supermassive black hole, or it will be matter falling into the black hole. And if a black hole is really infinite gravity for its event horizon distance, then it's not going to get any more. It just is what it is. So either the loss due to jets or the loss due to things collapsing in should cause the gravitational effect of a central supermassive black hole to decline at a certain point. So if you have a more mass or greater spin at the center, then the distance at which you have this plateau should change. And if it was dark matter, your shell around the galaxy wouldn't have that effect. So if you find it different for different galaxies, then you've got something other than dark matter to deal with. Think of it as a satellite in geosynchronous orbit. The weight of the satellite, the orbital velocity, it gets to a certain altitude, it doesn't need to go any further. It's just going to be there. Its energy is going to plateau. Same sort of thing. Doesn't require a variation of Newtonian physics. So in conclusion, there is this plateauing of stellar orbital velocities that's observed. Absent other direct source observations, they've come up with these things called dark matter and MOND. In the case of MOND, we have a gravitational constant that, they're ignoring the fact that it should be reevaluated, given that we now have awareness observations of more orange and red stars than we first thought in the Milky Way. So maybe there's a simpler explanation that doesn't require dark matter or MOND, and that's why I've coined galactic gravitational retention threshold, or GGRT. It would explain the Kepler slowdown to a certain point and then plateauing. Anything that had more energy than that would probably achieve escape velocity, and that's these rogue stars that we see between galaxies. And I think they evaluated approximately 700 of those that have left the Milky Way and are on their way out. They've had enough escape velocity to leave our galaxy. But only time will tell as to whether what I'm spouting as a postulation turns out to be real or not. We might need new instruments, kind of like hey, we couldn't take pictures of things in ultraviolet until we had ultraviolet sensors. I'm not a modern day Kelvin. I don't have the street cred that Kelvin did. I don't have things named after me. I'm just a guy that learns things. I'm just connecting dots where I see things being obvious. And as that Occam's razor thing once said, maybe the simplest answer is the simplest answer. So we'll wait until technology catches up. And I've got lots of links with very interesting titles to papers like Indefinitely Flat Circular Velocities and the Baryonic Tully-Fisher Relation from Weak Lensing. If you have insomnia, that's a fun read. And then no, we don't think elliptical galaxies have dark matter. And then, oh yeah, they do. And then the ever popular Fritz Zwicky, have to have him in there, if only for his name. And this I thought was interesting, the ultralight dark matter. There's actually a paper from the Max Planck Institute for Astrophysics in Germany. And then those people that aren't familiar with the Hertzsprung-Russell diagram, what that's all about. And a couple of videos from Sabine Hassenfelder on flipping back and forth over the last couple of years. Does dark matter exist or not? Do we need it or not? What is MOND? Is MOND got it right? And then if you're forgetting the long history in astronomy of the Earth is the center of everything. No, wait a minute, we go around the sun. All the stars go around the sun. Wait a minute. No, there are other stars that don't seem to be orbiting the sun. Oh, look, there are these fuzzy things beyond the Milky Way. What are those things? Oh, goodness. Those are not nebulas that are on the Milky Way. Those are actually other galaxies. And then for those people that are not familiar with the physics of a hammer throw. Okay.
That's how Thor flies. He throws his hammer and grabs it.
Yes. Yes.
Didn't Max Planck have an astronomy art have a page in astronomy magazine, Crazy Astronomy or something?
I don't know the specifics, but yeah, given the age of Astronomy Magazine and Sky and Telescope, I'm sure the one and only Max Planck probably had some articles in there with his name on them. But I know that there is an observatory, there is an institute, and there's actually a satellite that all have Planck's name on them. And whenever you think about the biggest that could ever be, Planck's name is involved. Whenever you think of the smallest or lowest that could ever be, Planck's name's involved. So they're all just limits named after him. All I know is if GGRT is real, it's hammer time. No? Okay. So had anybody encountered MOND before? See? Learned something new. Everybody might have heard of dark matter, but didn't quite know what it was or what it was based on or why do we need it or how much of it is there really. And the more they find it is kind of invisible and undetectable, the higher the percentage of the universe is supposed to be made up of it. Because you can't move things the size of stars with the wimpy things. If it's going to be wimpy, if it's going to be ultra light dark matter, then you need a massive quantity of it in order to control the velocity of stars on the outskirts of galaxies. So it's got to be a lot of it, right? Okay, was it too esoteric?
Just the right amount.
I did not get into the mathematical formulas of cosmological constants. I looked at the math of that and went, no. I also looked at the computer simulations for dark matter versus cosmic microwave background, and no. Okay, any comments or questions before I stop recording? Hearing nothing.